My name is Jennifer Bourgeau. Welcome to the Globe US Partner and Teacher Community Water Coolers. These are weekly events where we get together, we have a short discussion of a particular topic, and then just like at the water cooler, we see where it goes from there. And this week we have Peter Nelson with us, who is going to be talking about Landsat. Really exciting because 9 just launched, right? So it's perfect timing for us to discuss what we can do with that data that we'll be getting from our newest eye in the sky. And so I'll turn it over to Peter, who is also a Globe Partnership out in the western half, the northwest of our great United States of America. So with that, I'll turn it over to you, Peter.
Thanks so much, Jen. I really appreciate the opportunity to be here and to talk about something that I care a lot about and our partnership cares a lot about, and is part of what actually brought Oregon State and our College of Earth, Ocean, Atmospheric Sciences to the GLOBE program, is in part because of the Landsat satellite and the data that's been collected by the GLOBE program since 1995, 1996, when Dr. Russ Congleton helped to create this land cover protocol specifically to help with Landsat-based satellite research. So, GLOBE has had a really long partnership with the Landsat constellation of satellites and the data that's coming back from them. And what I really want to highlight is this new era of Earth observations that we're moving into. And Landsat 9 is sort of the thing that represents that. Continuous observations for long periods of time, working with other nations and other satellite systems, and helping to reveal patterns and processes around us. And so it's really kind of incredible to think about all the people that came before us, including Jen, actually, and like I mentioned, Dr. Russ Congleton, but also all the other people before the GLOBE program who really helped to set the foundation for doing remote sensing from space. That included people like Dr. Virginia Norwood, who helped to create the sensor back in the 60s, and that people realized had some capability if you put it into orbit. And so I just kind of want us to all recognize one of the values of the GLOBE program that I find is the generational science that we get to do together. And the database that holds all of our records and all of the measurements, the effort that people have put forward is really valuable. And it represents people's time, but it also represents landscapes that may not be there anymore. And so, what we're going into this next year with Landsat 9 and some of the data and science that people are putting out is really this exciting opportunity for the GLOBE program to reconnect to the Landsat science and the data that's coming out of that globally. And one of the things that is changing from back in 1995, 1996 in particular, is we now have wall-to-wall global maps at 100-meter sort of pixel scale all around the globe. That was something that GLOBE was trying to help produce early on. We now have more data than we know what to do with. So for me, as a GLOBE partner, what I think about is how do I help people understand that data that's coming out from all these scientists who are making predictions and telling us how the world is? How do our GLOBE measurements relate back to that? So I'm going to highlight a particular tool that connects all of us in the continental United States. Sorry, Elena up in Alaska, but we're getting there eventually. People are still working on that giant expanse. But for the continental United States, we have a data set that ties all of us GLOBE partners together, the US GLOBE partners. And scientists are working on expanding this out to the rest of the globe. And I would anticipate next summer seeing very similar data out there for all the globe and all the globe countries that are out there. So if anybody is looking at this and wondering, why don't I have that in my country? People are working on it, and sit tight. I'm sure that we will be getting to actually releasing that data soon. Nepal just had similar data released just this last week by a collaborator here at Oregon State University, highlighting the forest changes in Nepal. So what I'm going to highlight here is possible for everybody to take part in. And so I will just start off with, I think, a sort of the framework, right? Like Landsat isn't just one satellite, Landsat 9. It is actually the series of satellites. And starting in July 1972 was really the first measurements of Earth that we'd ever seen from space. Unfortunately, the first number of years of the satellite, it was actually in a different orbit, a little higher up in space, and so the pixels aren't the same size as what happened with Landsat 5. And Landsat 5, you see the length of time that it was able to collect data. And this is really important because this is what revealed the power of time series. The ability of satellite observations to monitor the same place with the same sensor over many years. And from this, people I've been working with, starting back in 2005 here, have developed the tools to synthesize all of this data into something that's meaningful for us. Because this is a lot. I mean, millions of observations, a lot of computing power. So for us, I want you to start thinking about Landsat 9, this satellite that is collecting data right now. It's starting to wake up. In January, we will start getting new observations from space. What are we going to be able to do with that as that comes in? Because we have Landsat 9 and Landsat 8 that are in opposite orbits, that are actually able to see the ground for every 8 days. Phenology, we can actually map that really well with the same sensor. Changes over time can actually be integrated all the way back to 1972. So I think there's this great opportunity as we look to the 50th anniversary of Landsat, the Landsat mission this next year, to really put our GLOBE program measurements into this longer time series. And we started in our lab working with teachers, making climate change relevant in the classroom. And we developed a lesson that had students actually looking at time series Landsat data and trying to understand the changes over time. And many of you might be familiar with this now because of the new Future Forest lesson that came out, right? And that actually was based off of this work that's presented right here. And I would like to play this so that we get a little context to what we're doing today. And as you watch this video, it is on MyNASAData. There is this lesson plan, a hook at the very beginning that helps guide us through how you might be able to use a lesson like this in your classroom. So with that, I'm going to hit play and see what we see.
My name's Robert. Earth and Environment University. All of these images are numbers. Now we can display them on a monitor as different colors, but what we work with analytically are the numbers themselves. When we're looking at how processes affect landscapes, you need to understand how the processes unfold over time. Hindsight's 2020. Landsat gives you that hindsight. In the Pacific Northwest, known for its timber, right, for producing lumber. So you've got a stable forest, and it looks kind of the same to the satellite over time. Then you come along, cut down all the trees, boom, it's a lot brighter. And so you can think of subtracting one part of the information. And the other thing is that you've revealed something new, which is the soil, the rocks. We added this soil in there, this signal that it sort of bursts out at you like a flag. That soil signal that was there, that you saw right after the clear cut, immediately starts getting obscured. Grass will come in, shrubs will come in. So as that happens, the soil gets covered up, and so you can actually watch that whole process happen from an older forest to this bright soil to recovering vegetation. So the progression in the bark beetle is we have a fairly stable lodgepole forest. There'll be sort of an explosion, an epidemic of these beetles. Our color scheme kind of goes from stable forest, which is in tones of blue, this bright red coming from the soil and from branches and things that are revealed when the trees lose their needles and when the needles change color. One of the insects that's increasingly important is a western spruce budworm. They don't go in and kill the tree outright, but come in and eat the buds or the young needles off a tree. And so the satellite sees that as a bit of a darkening of the picture over time. By the end of the time period, we see pure yellow, and that's associated with broadleaf shrubs. It could even be a shrub field, just dense. Those bugs have changed the environment for everything else there, and the everything else there in this part of the world are shrubs, rhododendrons, other shrubs that are usually hanging out in underneath the trees where it's kind of dark and shady. Boom, they get all this light, they love it, they grow like gangbusters. One of the interesting things about managing forests in the Pacific Northwest, you can see a very strict delineation on your landscape from the satellite's perspective, and that's just a manifestation of the policy differences, of the ownership differences. The idea behind science is to develop understanding, ultimately to be able to predict, understand process. When we look at a change, when we look at those graphs of life histories of individual pixels, it's that the numbers that drive everything. It's the numbers that we use to look at how severe things are. It's the numbers that we use to quantify how long did it take, or when did that start, or how big was that clear cut. The Landsat perspective is really the only tool that lets you look at what's going on at the scale that you're interested in, where you can see individual events, and harvests and roads and houses, and at the same time look at the whole landscape.
Well, as always, I appreciate that piece. I appreciate that piece of information that has shared, and what I want to highlight is these sort of questions should be guiding what I'm going to present to you in a moment here. Understanding what Robert highlights, there's ways of extracting out fast processes and slow processes out of the Landsat archive is fundamental to the science that is happening today. And what is important, and the role that we all have to play, is actually localizing this information and helping to give it some meaning. So what is this what are phenomena that are happening around us that happen at fast speeds? I think of like forest fires that we've been experiencing out here in the West, in the Western United States, but also hurricanes or other sort of floods or natural disasters are typically those fast sort of changes that might be happening. Urbanization. But as Robert mentioned, these slow processes of insect outbreaks, of drought, even of ice storm damage to a single tree that takes 2 or 3 years for that tree to actually die, is one of these things that is captured in Landsat, in this record. But we really don't have a lot of information to validate or to really understand these historical events. Now, if it's happened in the last 10 years, our databases are pretty good. But as you go back in time and get closer to that 1984 period, our databases are less specific and events are not in there. So this is where local knowledge from the Globe community can really help us to understand and to move the science forward. I'll highlight that our lab has created quite a bit of animations and tools and maps to look at these changes over time. So, we've synthesized some of this, and it can be really useful to have some direction. So if you're interested in national parks, we've got a park trender. If you're interested in cities and urbanization, like Kevin Sykowski and the whole urban heat island campaign, you might be interested in our city trender. And then we have a couple other areas. Las Vegas is always the example people talk about with change over time. But we also have this really incredible tool that allows you to look at the whole continental United States over time. And wow, pixels are changing. What do they mean? What's actually happening? You'll see a little bit of our bias of sort of where we want to focus here. But this is a really valuable tool that you can, if you right mouse click, you can actually get your controls and you can pause this and actually look at it, right? So when you look at a map of the United States in land cover form, you should be seeing some patterns here. And in 2004, we see, a distribution of trees that are green out here in the Pacific Northwest. We see in the central part of the United States, the farmlands. We see the Rocky Mountains and Denver actually popping out in the red right in the middle there, that urbanization. And we see the nice deciduous forest of the Northeast. So this is a tool that we've been using to actually take and show you land cover over time, which is derived from that satellite data. And so we've worked with, let me go back up to the top here, the U.S. Forest Service to develop and actually share the data that our lab has been producing. And it was part of the system called the Landscape Change Monitoring System. And like I said, I've been working on this for about 15 years now in various fashions. And so Warren Cohen was my supervisor who helped to do some of the early Landsat mapping of forests. And he used shadow as the way of looking at how old a forest is. So, there's been a lot of research, especially around trees and tree change and forest change. So if you're part of the Trees Around the Globe student research campaign, that's how we, kind of connect. We can connect to that really easily. So if you want to learn a lot more about how this works, what it does, please have your students read this. There's some technical terms in here, but you'll see that there are right now at least 3 different science algorithms that are trying to find patterns, and they don't agree all the time. So scientists are really needing to have this local knowledge. And the great thing about this is all of this data is available for download right here from the Forest Service database. It is also already available in ArcGIS Online as imagery layers. The other thing is you can view it. And so that's where we're going to go right now, is this Landscape Change Monitoring System Data Explorer. And here you'll see a lot of information. And if you have looked at the Future of Forests lesson at all, it uses this to explore some of the forests and some of the reference data that is provided that is otherwise hard to access, right? So I do recommend launching the tutorial and go through the tutorial. There is a lot of information here. And so it can be very overwhelming. But the key that I want you to walk away with is there's things that are happening out there on the landscape, patterns and processes. They're getting measured by Landsat, and maps are getting created. What do they mean? Requires you to investigate and actually go to these locations. Nobody can actually tell you exactly what is happening in that particular pixel. Many people have not looked at every single pixel. This is all algorithms and math. And so this is the science opportunity that we have together, is to look at pixels that nobody else has looked at before, to then go there and make our observations, to understand what the heck is happening in this river is where we're at, right? And so, this is part of the data literacy piece. Data's out there, and we all have to start to understand how to work with it. Okay, so this is so just an area that I've been working in a little bit along the Missouri River with a community here at Nebraska Indian Community College, and we've been investigating some of the flooding that's been happening in the Missouri River. And again, we don't necessarily know much more than somebody made a pretty map, right? And so, as Robert mentioned in that intro video, there are these different pieces of information you can pull out of the Landsat time series for a particular location over time. You can look at it as an area that is no change. And so the measurement, it stays green the whole entire time, or it stays yellow the whole entire time. That is our null hypothesis, no change. The pixel color stays exactly that same color. You know, an area, for instance, here is, we are able to zoom in, you know, an area here is forest, you know, showing up as green. So, you know, we would expect this area to maybe be stable or not have much change going on, especially because we're not getting a pixel that's highlighting in that area. Okay, so part of what I want to highlight is you don't have to know the answer to go and investigate these locations. Really, you can use this as a guide to say, well, something is happening here. Let's go and investigate. As Robert Kennedy was describing, it could be something that happened really fast. And that might be what is illuminating this location. Or if we turn off that, or you can also slide that bar all the way back here to turn it transparent, you notice that all of those areas, those pixels, go away because those were all fast changes of some sort. I don't know what, I don't have the information. I don't have any measurements. I don't have any photos. I have nothing to tell me about why that might have happened. But here I'm able to see, well, there's no slow change that might be happening, right? And as I zoom out, you see a lot less of the slow change on the landscape, okay? At least here. And so if we, on the other hand, I am gonna pick on Mike because I see him here. And let's go look at Fredonia, New York, right? And so the nice thing is you can just type in any address and go there and start investigating what's there. So this is helpful. I get a nice high resolution satellite image. Coming from where? I have no idea, doesn't really say. I also don't know what year this is. So those are important things to consider as you might investigate a particular location. Dates and time is really valuable when you're looking. And so if I turn back on the fast loss, wow, Mike, your area has had a lot of fast change, but not very much slow change, right? And so can you tell me what might have happened that were fast changes in your area?
Yeah, building student housing, removing vineyards and replacing them with something else, or taking forests and turning them into vineyards.
Yeah. Oh, yeah. Like here, the vineyards of Fredonia. That's
it's a housing complex. It's a housing complex.
Ah, see, I wouldn't have guessed that, right? The name, like, see, so this is the lack of information and context that I have being out in Oregon. I need my globe partner on the other side to provide some context, right? And this is the kind of information that I might be able to deduce if I turned off this layer or, you know, turned that down. Ah, okay, yeah, that's housing. It's not the shrubs or vineyard lines, right? So I might have gotten there eventually, Mike. But what's great about this, right, is when you turn this on, one thing to note is you actually have an indication of the year that the change happened. So these lighter colors, as you see in the legend, are older changes. Most likely those won't be in the globe database. We won't have any measurements right up until about 1995, kind of halfway in here, when Jen and her team like started actually getting the data to help us to understand a map like this, right? So, you know, this is where it would be excellent for Mike. I'll give you this assignment, right? It would be great to have a picture in this location here, right? So that if we actually go to the globe database and how do I find Fredonia to begin with, right? I don't have a search bar. So I have to somehow be able to read this map, right? And understand the place. And one thing I'll point out, you have a longitude, latitude coordinates at the very bottom of this that you can use to find yourself. And importantly, you want to use to find maybe the data over here in the database. So I know Mike's over in this part of the world, right? Somewhere in the New York area. But if we come over here and look for what kind of globe photos might we have at this point, It's going to take a little moment to run. And okay, so I see some, you know, some areas, but all right, let's zoom in, right? So to me, this is one of these challenges of trying to situate the Landsat and the science data within the GLOBE program, right? My interface here, just I can't find where, Mike, where am I? Where's your photos? Or have you contributed any data? I can't find you on the map.
Little southwest of where you are now.
Yeah. All right. Am I getting closer?
You are. Keep going.
All right. Little geography hunt, right? Ah, okay. Finally, Fredonia. I've got that place on my map. So, you know, now I can actually zoom in and try to find, okay, so at least in the last year, Mike, I'm only getting a couple photos over here in the parking lot, right? Well, that's pretty useful. If I look at, if I orient myself to what Mike is showing us here, the nice thing is we have this nice circle, really obvious mark, right? So let's go back here, and I am going to just kind of navigate over a little bit. I might even zoom myself out. Oh, okay, perfect. Here is that nice round circular unit. I see the parking area. Nice. And if I zoom in on that location up here, interesting, we're going to get a little change polygon that happens, right? So this right here is one thing you're seeing is the 30-meter pixel of a Landsat. The other thing that you'll notice is that sometimes the pixels are kind of weird and they don't quite line up with the features underneath, right? That's the resolution of this particular satellite. These are the pixels, right? This is also why your GLOBE measurements may not line up exactly with this satellite data, okay? So what's nice about this is I can get a little bit of information from just looking at this map and doing this. I can get even more if, you know, by going to the GLOBE database and clicking on one of these photos. And then I can actually look at it and go, oh, okay. To the west, here is a group of trees. To the south, that's sort of what that parking lot looks like, right? Okay, to the east is some more trees. That's kind of what that looks like. And so I can actually use that to sort of orient or understand the context of these pixels. What is really useful is if you go down to the tool button here, you can actually query this. So instead of just relying on your eyes to say, okay, this is orange, well, it's sometime during this time frame, right? This weird legend. You can actually go over here and say, query the visible layers. And I can just get the question mark icon and I can click on it and it will run. It's running right now to get the information. Right, you got to double click. Single click won't get you. Double click, it's now actually running to Google's Earth Engine to get the information to tell me that this parking lot was created in 2003. So Mike, with your local knowledge of this area, does that sound about right?
It does.
Yeah, so 2003. Think about this. Mike had really just started his GLOBE measurements at the time that this parking lot came in, right? So Mike, have you measured the surface temperature of this parking lot?
I have not, Peter, but gosh, I wish I had.
Right. I mean, has it been getting hotter over time? How did these trees relate to the shading of that area, right? And importantly, what was there before 2003? Was this actually an area that was grass or trees that might have been cooler if you would have been doing those surface temperature measurements, right? But now it has a whole other temperature and it changes the radiation budget of that area, right? It changes the whole dynamics. So how does that affect these trees that are right on the edge? I don't know, but now we actually have a date that can tell us maybe how fast these trees have been growing, or importantly, how the systems, the Earth system in this location has changed at a particular date, right? So this was the bottom of that V that Robert showed in that video. You know, when we have disturbance, we lose photosynthesis. We lose the ability for that area to reflect the light in a particular way. And so that change is what we're picking up here. So there, that was really interesting, right? We got a date. That makes sense. That makes this legend a lot easier to work with. And I can pop over here and say, well, what happened in this one little pixel, right? And here we should see a more recent date. Oh, a null. Well, what does that mean? I got null data. Is that an error? Maybe. So, that this is really interesting to see the way that it's querying this location. And I've got a different square underneath it. So we have actually some map alignment issues that might be popping up. Again, this is an error in the model that requires an investigation and for us to maybe help the scientists understand, why did they get this? What happened in this location? And that kind of thing. So that's one way that I use this map to just explore an area. But one thing that I want to highlight as well is if you query the LCMS time series, the Landscape Change Monitoring Series time series, you can look at the whole entire record. So I'm going to come over here where I feel really confident that I'm in the parking lot. Again, double click and let it run to Earth Engine. This takes a lot longer because it's grabbing 40 years worth of data and then it's processing it, doing a little bit of work for it. So you can see this is the Google Earth Engine cog. Oh my gosh. All right. We have a graph. What does this mean? Data literacy is all I'll throw out to you guys. This is a chance to actually understand what Robert presented in that very first video in your local context. What's important to show here is that the developers are putting lots of information on this all at once. So we need to simplify it. And what they're showing is that slow loss value that we had on the map, the fast loss, and then what is the chance that it might have actually been going up? Their model was wrong. The nice thing is you can actually just turn these off and now we have nothing on our graph, right? But what we noticed in that parking lot is that we had some fast loss, some fast change. So what is happening here is this is the model looking through the Landsat record to say, is it changing here? And what we notice is that, well, the model kind of said, something might have happened in 1992 to 1996, but we don't know. We're not really confident. It's really low confidence, 10%. But, here, something in 1999 to 2000 might have happened. We had a different satellite. Maybe that caused a change. Don't know. Mike, maybe they started actually, clearing that area, in 1999, and they didn't actually get it paved until 2003. All I know from this graph is something happened during this time period. That requires the investigation, getting more information, right? And then something else happened. There's, the model is making some predictions. And so this is kind of telling us how confident Robert Kennedy is in saying an area changed. Okay. What I want to highlight is that you actually can see the raw satellite data. This is actually the numbers that Landsat was measuring each year for that location. And it's just going up and down, and I don't know what the heck is happening, right? Pay attention to the scale. Maybe that has something to do with it, but maybe not. So what Robert shows and demonstrates in that video is linear segment fitting. So what we try to do is just take this really complex signal, a linear segment. So can you describe this with that null hypothesis just the whole way? Or are there influential years that are known as breakpoints? And what we see is that in this location, we see some increase in some value and then some decrease in some value. Again, what this actually means, we have to have measurements on the ground. And Jen will demonstrate this over and over and over again if you look back at how to classify a satellite image. And it talks all about getting that ground reference data. That is the Globe Land Cover Protocol. And that's the kind of information that we need to actually understand a pixel signal like this. And so the investigation can be flipped now, so that this data drives some of the investigations or the protocols that you might select. And your own knowledge of past dates of changes might also influence what you might investigate and how you might go about it. I want to highlight that you can download this data. So you can actually have this data to do your own analysis with. Do this for 30 areas. You don't have to go anywhere else to get the satellite data. You can just download a comma separated file, and you have the raw Landsat values for that pixel over time. You don't have to go anywhere special. You can just come here and get that. The other nice thing that I'll highlight is you can create this chart or print out this chart and use in your presentations or other things like that. So, here you can see, here is the actual raw satellite data. Here's what we predicted to be there. And then here's some probabilities that were right. Here is the model data. It's no longer hidden behind anywhere. It is exposed to you for every 30-meter pixel across the continental United States. So I'm going to stop right there because there's other things that we can do with this, but just that little bit of information, I hope will get you to move beyond just thinking about forests and forest change to thinking about all lands and all of the changes that have happened over the last 40 years since 1984, and Landsat 5 first started collecting this type of information for us. And what information can your students or your community understand by looking at this type of data? So I appreciate those that did show up today, and I'm going to stop right here, and I'd like to have a little bit of a conversation or some questions about how others might want to use something like this.
Well, it's very cool, and I think you remember this. Those pixels that you highlighted off that were from we tried to pick off the points off the LCMS, right? So some of the misalignment could be just, I tried to pick the center of the pixel, right, and get the lat long from that. But no, it's a very cool tool. So.
And Mike, you actually brought up something that is really important, and this is a shifting change of the GLOBE program, is the technology, right? The GPS and the way that we located ourselves or located yourselves back in the year 2000 is very different than what we can do today with the Globe Observer app and the mobile technology. So we do want to really need to be thinking about the location of our data points and make sure that we are checking them as they go into the GLOBE database. Because when you overlay that with a 30-meter pixel, if you're off, you're going to miss the label. You're going to be saying that they're wrong when you're actually wrong, and vice versa. So, I think another opportunity here is to review our own data in the database in relation to these change areas. And for the more historical data, and I'm looking at you, Jen, because I'm kind of curious about these older ones, what has changed in those forested areas that you and Russ were measuring in New Hampshire, right? And this idea of processes rather than a state. A forest is actually a process that is happening and growing. It's not just a state that it stays in. And this is a little bit of a shift that Landsat has opened up and given us the ability to see, is the process of forests and forest growth and succession, not just a point in time. Trees are there, now they're not.
Peter, something cool that you hit on earlier was, when you were showing New York and, about the vineyards. And I think that's super vital because, you know, you didn't know what it was. I mean, I'm assuming that you assumed it was a vineyard at one point or another. And then Mike's like, no, it's an apartment complex. And, you know, that's why GLOBE is GLOBE, because because not everyone just reviews or looks at the data that they've collected. Okay. What we really want, you know, with the whole data literacy with GLOBE and NASA and all that, we want people to, you know, yes, we want them to look at their local environment, but we want them to step out of their locale and do some comparisons in other places of the world. And by having someone, you know, in another part of the world being able to identify what try to identify what you think is what you see might be completely wrong. And, you know, Peter and I have been working, I think, almost every day this week, you know, working on our stuff with the trees campaign in year 4. You know, the whole idea of the location accuracy is really important because, you know, as you know, with the trees campaign and some of the other campaigns and what Peter's talking about, this comparison of the GLOBE data to the NASA, you know, satellite data, airborne data, you know, like instrument data on ISS, like JEDI, things like that. All of that stuff, when that data comes back to the satellite or instrument, that's all geolocated. And if you want to do a comparison between that and, you know, what GLOBE, you know, the observations you took like of tree heights or land cover for GLOBE, and you need to do a comparison, you need to know that what the GLOBE data is that is matching up, the geolocated, you know, lat long is matched up to, you know, say ISAT-2 or Landsat or whatever. I mean, that's why, you know, that's why we have to really scour this with like a fine-tooth comb to try to figure out, hey, and that's what we're doing with the trees campaign. So, you know, I'll leave it at that. You know, I don't want to take up too much time because it's, yeah. But thanks, Peter.
Definitely, Brian. I appreciate that pitch in there. And I will highlight that, you know, one of the first things that has to happen before we can map the biosphere or the Earth is we got to get rid of that atmosphere and all those clouds. Like this is actually foundational to what we do. And so, you know, I appreciate the cloud folks and that team, you know, but, you know, as soon as they do the atmospheric correction and the removal, we can actually see the true reflection off of the surface of the Earth. And I'll point that, in fact, it's the cloud masking piece where we get errors. And so if you're in a location that has a lot of summer clouds, you might actually notice areas that are identified as change, but technically are really cloud masks or bad cloud identification. Cirrus clouds, really bad for this. So, you know, I want to encourage you, when you do land cover or tree height observations with the Globe Observer, also do the cloud observations. It's really important to make sure that we are doing a good job atmospherically correcting our data so that what we are saying is changing is actually changing, and it's not atmosphere particulates, that piece of things. So there is a really strong connection and a need for atmospheric correction and the atmosphere protocols to be done at the same time as we are doing our biosphere measurements with that. I will also highlight getting the cloud measurements down to 30-meter locations is vital. Otherwise, those cloud masks or the measurements that are made in the cloud protocols have no help for us at 30 meters. They're going to be in a different location. We're going to be talking about different clouds. So we cannot evaluate the quality of the cloud masks, which again is one of those errors that is in these maps that I've been showing you today. And when you think about glacier change, that's where we see the most error from clouds. What's the difference between a glacier that's bright and cold, that's high up on a mountain, and a cloud that's up high and cold up in the sky? A lot of times you think it's a shadow, but you know, that's a place that we've seen a lot of errors. So, you know, that cloud part and cloud aspects is really important for our success in the biosphere. So I want to mention that because it's Earth as a system. And as we think about Landsat and the 50th anniversary of Landsat, it really was the foundational satellite that said, we can do this really well, we can see these things, but oh, we are missing these aspects. So we need to build a ISAT-2 satellite that will actually do measurements of laser and do the structural measurements. Oh, we need to see through clouds. well, we need a radar machine that will actually do that. So Landsat really not only showed us the potential, but also all of the pitfalls of remote sensing from space. So join me in exploring this map and starting to celebrate 50 years of Earth observations from space.